Hello and welcome back to the second lab application of this lecture. Uh, in in this lab application, we're going to work on the coupled modes again, but this is a slightly different problem. The previous problem only attended the case in which you had a notch and there was a dielectric disturbance, perturbation, and that would change the mode coupling from the 0th order to the 2nd order. There would be an intermode coupling. In this case, we are working with a slightly different problem. Like, the main idea is to find out how much of the light, the input light, would be coupled to the other branch. So let's say that we are applying the field, electric field from this port, the light, and nothing from this one. So we are interested in finding what would be the fields at the output here. So as you can see, we have two identical waveguides with these refractive indices, and we have a separation of 4 micrometers, and the operational wavelength is 1 micrometer. We're going to be using another MATLAB code. This is going to be the second version. And all we need to do first, as you now know, is to find the unperturbed modes for the 0th order. I already found the propagation constants for that, and let's try to do the same with the MATLAB code. So here is the MATLAB code. Let's try to run it. I hope the connection will be going good smoothly. Okay. Yeah. It's taking a little bit of time because of this lag due to the connection problems with the server. Really sorry about that. In the meantime, as you can see, the code has been arranged in a very similar fashion, right? So we have to first find the unperturbed modes, and we're going to be doing the same things, but different from the previous one. We're just interested in a single mode. That's going to be the 0th order mode of the identical waveguides. Right, so it's stuck here, so I'll just pause this video for a while so that the code will start running soon. Okay, so I just waited for it to respond, and now it's showing us the same thing, so that we are very familiar with. The mode is around 1.95 times 10 to the 5, so let's just get rid of that, and 95. Okay, so this gave us everything together. Let's look. All right, so now we're seeing the modes. So this was our original mode, all right? So this is in terms of meters, of course. The original mode was the blue one, and these are the unperturbed modes on both sides, all right? Let's look at the PowerPoint and a little bit into the equations. So we found the unperturbed modes, but what's next? And of course, you have to write down the perturbation, and the perturbation is going to be coming from the first waveguide mode. That's labeled as 1. The second one is shown with 2. So we cannot really excite the backward propagating modes. So that's because of that, we'll only be interested in the positively propagating modes, which have the same phase information here and there on both sides. What's more, well, that's why we're left with this, and the tail of the evanescent wave in the input waveguide, the first waveguide, will perturb the mode in the second waveguide. So that's why this is written as N2 minus N1. in this case, n2 square minus n1 square. And if you do this calculation, you'll find the coupling coefficient K12 from the first waveguide to the second waveguide, and we found it to be like this. All right, so let's look at this in our MATLAB code. Remember, we have to find the overlap between the first waveguide mode and the second waveguide mode. These are the unperturbed waveguide modes, so we have to basically understand the overlap here that's shown here for the unperturbed modes. All right, so in order to do that, you have to be very careful, and you have to give the offset correctly for the second mode that's shown as mode 2 here. And the Simpson's integration model is actually looking into that, first normalizing it, and after finding the normalization, we are looking into that overlap between the two waveguides. So that's why we're multiplying the two waveguides here. All right, so after calculating that, we will end up with the coupling coefficient, which is also shown here in that working space that I just mentioned. Coupling is 3.6184. Let's look at the PowerPoint slides. Yeah, so that's where it's coming from. And now we can write the same thing for the first one too. So is it going to be only the first waveguide to the second waveguide? No. Once the first waveguide power is depleted and transferred to the second one, the same thing will happen for the second to the first one. So the second waveguide will now be the perturbing factor. Everything is almost the same except for the fact that now we have A2 here. Okay? And epsilon 1, epsilon 2 is again the overlap of these two are searched. All right, so now we go back, and we also realize that, I mean, I didn't mention it, but we realized that the propagation constants for these two identical waveguides are the same. So that's why the K1x and K2x are just canceling each other. And we also know that if we calculate this K12, we will also end up with K21 because they are identical, right? So we end up with these two equations, actually. So if we look into it, we can further derive this as like this strongly coupled case, right, from A1 to A1. And we initially know that A1 is 1 and A2 is 0 at x equals 0 point. That's the initial point. So we could really have said, just to be consistent, minus A here. It doesn't really matter. And as we're moving on, so as you can see, for that to be satisfied, the initial position is 1. We need to, for this kind of a solution, the second derivative is equal to itself. We have to only have the cosine 1. And if we put that into the equation after solving for the first waveguide, we see that for the second amplitude, we have this sine. So they're like alternating, and they have a 90-degree phase shift, and that's how the power is actually transmitted. And here, I just wanted to show how it looks like. This is our initial waveguide. We start, and it gets coupled to the second waveguide and then coupled back. So that's the top view, and this is how it looks like if we look at from a certain angle. So in three-dimensional space. So Z is this distribution, and X is our propagation distance, as you know. We're looking at the absolute field here. All right, just looking further into the code a little bit. The code also does the same thing. After finding the coupling coefficients, we're just plotting the power that's been coupled between, so the cosine and the sine terms here, and I'm just like taking everything into the memory to come up with that three-dimensional code, right? Which looked a little bit fancier and gave us a little bit of more insight. So for every position, I'm multiplying the amplitude with the waveguide distribution, all right, for the mode that was calculated before. And then I'm just using the surf code to look into this three-dimensional code, because this will now have a matrix, and I'm looking at them together on the same plot. The two surfs are done together with the hold command, for just like in the case of one-dimensional plotting. All right, so this looks all fine, but instead of doing this with MATLAB, I'm just gonna drag this to this place, and here, this one here. Okay, so that's what I was looking for. All right, so this is called COMSOL. That's COMSOL Multiphysics. That's a very useful numerical analysis simulation software, and Penn State has a license for that too, so thereby I can show the results to you. They're now investigating a coupler here too, so it looks like this. So it's slightly more advanced, because this is not a two-dimensional thing, but it has three-dimensional activity here. I have the waveguides here. As you can see, the two waveguides are propagating next to each other. There's a slight coupling region here from this waveguide to the other waveguide, but in the end, okay, so let's zoom out a little bit to see it on the same. All right. So at the end, as you can see, it's the same thing happening here. Just like we plotted for the other one, the initial waveguide with our MATLAB code, the initial waveguide's light is being transferred to the second waveguide, like you can see here. All right. What else can I show? Let's continue with the PowerPoint slides a little bit more. So I wanted to show you an animated picture that was taken as an output of a numerical study, again, and another simulation, basically. This time, another software was used. It's called RSoft Synopsys Optical. But currently I don't have the license for this, so I can't show you a simulation, but at least I can show you a prior simulation that I had done several years ago. Now the light is coming from one of the waveguides, and at the end of the simulation of this GIF file, please click this one to view it better. When it says animated picture, it's gonna be hopping to the other waveguide. So this is how the couplers are actually designed. So let me do this, and then hopefully you can see here that, yeah, so the waveguide, my mouse cursor was showing you what the results were when I had run the simulation. So we see that the initial light is being transferred gradually to the second waveguide. Okay, so this method is called beam propagation method, BPM. That's another way of solving the Helmholtz equation at every point, Helmholtz wave equation. Okay, so let's go back, and I also have another slide with, again, using RSoft. This is another animated picture. In this case, what we have is light is coming from this point. We have time monitors at every point, different points, and look at it. So the light is coming from here, and it's circling with the help of the resonator, and it's getting outside from this side. So this from this branch. Okay, seeing it once again. Yeah. So we're going to look at the two time monitors results here and there. All right. Okay. So these are called at drop filters, basically. So you put the beam from one port, and as a result, you have three possibilities, right? So this ring resonator will be resonating for certain wavelengths, and it will just couple the light very similarly like the couplers that we investigated to the other side, right? So the light should have certain wavelengths to resonate inside this ring, and it as you might already think, it has a lot to do with the diameter of this ring resonator. All right, I mean the geometry of the ring resonator. So this line, the data on this line will be dropped for some wavelengths, and it will be transferred to this side for again some wavelengths. All right. So, but how often does that take place? Well, we're looking at the two time monitors. The first time monitor is this one. All right, and the second one is this one. So light is coming here, as you've seen, and coupled back to this through port. So we're looking at the through port here, through channel, and the drop channel. So for some of the wavelengths, the light on the drop channel is dropping by, meaning that it's resonating inside the resonator and just hopping to the other side. So we see the peaks appearing. So this is a very useful filter if you think about it. Because the separation between these peaks or these dips are well defined with the help of this ring resonator. Okay, and you basically just eliminate that wavelength information from the channel, and you don't allow it to go to the drop channel anymore. All right, so let me see if I have any other. Yeah, maybe I can also talk about a little bit about this one too. So I did not run a simulation about this, but just like the delta function potentials, if you remember, if you just cascade a couple of these defects, what we have mean by the defects, well, we have these openings here inside the waveguide, and we will see that just like as in the case of cascaded n times cascaded delta potentials functions for the quantum waves, we see the appearance of stop bands here as well. So between that stop wavelength, whatever you have information corresponding to these wavelengths, they will be reflected back, just like in the case of a mirror. And the other wavelengths, which reside inside the pass bands, will be transmitted to this side. All right, maybe as the last thing, I can talk about the prism coupling too. Well, you know that you can never couple from the air, right? You need something extra to couple the light directly from air into the higher dielectric refractive index material, like in this case, the film here, because you need this total internal reflection to occur. To do that, one of the things that you can do is to put a prism, which will be critical in the upcoming lectures too, and then the leaking mode can leak into the film, and that can perturb the waveguide mode inside the film, and that can help us to couple some of the light at least inside the this film. All right, so that was basically all I wanted to talk about the second lab activity. Hope to see you in another one.